In this video, we're going to solve an advanced first order circuit. The reason why I call it advanced is you see we have a voltage source V of t here where they give you the graph, and what's happening is at t equal to 0, essentially the battery's turning on, we're getting it at 9 volts, but then after 0.3 seconds it's going to turn back off, go to 0 volts. So essentially we have one switch turning it on at 0, and then a switch turning it off at 0.3, which means we're going to have to go through our whole process of before and after the switch for each of those switching circuits. So let's see it as we go through it here. So the first time something changes is at 0. So we're going to look at what happens at t equal to 0 minus. So at 0 minus, we are in steady state, and at 0 minus, based on this picture over here, the voltage is 0, so it's a short. So we have 6 kilo ohms there. At steady state, the capacitor is an open. Then we have 4 kilo ohms here, 8 kilo ohms. So at this point in time, since there's no voltage source, or really voltage source of 0, and it's in steady state, there's no current going through there, everything's 0 here. So that means the voltage across the capacitor at 0 minus is 0 volts. Nothing's there going on. Now, as we look at t equal to 0 plus, now based on this graph, the voltage source is now at 9 volts. And we now have this capacitor here. It's no longer an open circuit. But we do know that it's going to have the same 0 volts across it that it did at t equals 0 minus. But what we're looking for here is we're looking at what is the value of the function V0 that we're looking for at 0. So what is the value of this voltage of this resistor over here? Now we have a little bit of an issue because since there's 0 volts across this capacitor, since these two resistors together are in parallel with it, means there has to be a total of 0 volts across those resistors. But because those two resistors are in series, whatever the current is in one is the same as the current in the other one. And the only way for the net result to be 0 volts is if there's 0 current. Another way of thinking about that is if we have a 0 volt here, this capacitor is kind of like a short in this case. So essentially all the current is going to make all the voltage drop on the 6 kilo ohm and nothing on the 4 or 8. So that means my V0 of 0 plus is 0. Now let's see what happens as we go to infinity. Now I sometimes call this fake infinity. And the reason why I call it fake is we know that that 9 volt source is not going to stay on all the way to infinite time. Once it gets to 0.3 seconds, it's going to turn off. However, if we want to figure out what's going to happen in steady state, we need to pretend that we do reach steady state to do our calculations, and then we can go back and modify it. So this is the fake infinity, the fake steady state. We have our 9 volt source, 6 kilo ohms. The capacitor becomes an open in steady state. Then we have 4 kilo ohms and 8 kilo ohms. And since it's an open circuit for the capacitor, nothing's going to go there. We can just use voltage divider here. V0 of infinity will be the total voltage times the resistance we're at, 8 kilo ohms, over the sum of the resistors, which is 8 plus 4 is 12, plus 6 is going to be 18 kilo ohms total. So that means we are looking at 4 volts for our infinity. So our initial formula here then is V0 of infinity is K1 is 4, V0 of 0 is 0, K1 plus K2, so K2 is negative 4. So V0 of t is 4 minus 4 e to the negative t over tau. And really quickly here, maybe looking at the part here we're in steady state, if you wanted to find the Thevenin resistance there, on one direction you're going to have 6 kiloohms, the other you're going to have 12. And so 6 in parallel with 12 is going to be 4 there. And if you do R times C, 4 times 100 micro, so 4 kilo times 100 micro is going to be 400 milli, so 0.4. 0.4 seconds here. So really quickly, the R Thevenin was 6 kilo in parallel with 12 kilo. That makes 4 kiloohms. And my tau then is 4 kiloohms times 100 microfarads, or 0.4 seconds. But the thing is, this formula would work perfectly fine. However, it only works until the second switch happens. So it only works between 0 and 0.3. Okay, so now let's see what happens at 0.3, but I'm going to go ahead and remove this in order to give myself some free space here. So the formula we had already was 4 minus 4 e to the negative t over 0.4 up until 0.3. So now at t equals 0.3 minus, so it's right before the second switch happens, we can take a look at what we have here. We know this is 9 volts, we know 6 kiloohms. We are not actually in steady state, so we put the capacitor in there. We have 4 kiloohms and 8 kiloohms. Now here's the thing, we actually know what the value of V0 is at this point in time, because we have the formula above, and we can go ahead and plug in 0.3 into that. Now it's a little bit of a pain to do this here, so let's see. We have 0.3 divided by 0.4 negative, and then we do e to that power times 4, and subtract that from 4, and we are going to get a value of 2.11 volts. So that means we know the voltage here is 2.11. But we don't need that. What we need is, we need the voltage across the capacitor, because that's the only thing that is going to stay the same on a switch, that's guaranteed to stay the same on a switch. Well, really we could go ahead and say, okay, let's find the current through it based on Ohm's law, and then we can find the voltage across this resistor and we'll add them up. But since that's 4 kiloohms and the other one's 8, it's going to just be half the voltage. So 2.11 divided by 2 is going to be, I'll round it to 1.06 volts here, which means my voltage across my capacitor is 3.17 volts. That's what we have right here. Now we can go ahead and convert this to right after the second switch happens. Now, in this case, we're not just disconnecting the battery, we're actually putting it to 0 here, which means it's still connected as a short now. So we have 6 kiloohms, the capacitor, and then 4 kiloohms and 8 kiloohms. Okay, and we know that the initial voltage here is 3.17 volts. And what I need to find this value of V0 right after the switching. Now in this case here, because of the layout of the circuit, the 8 and 4 kiloohm resistors are in parallel with the capacitor, not in series. Since they're in parallel, they have the same total voltage as the capacitor, which is actually what happened earlier. They had the same total voltage. So we can use voltage divider, and what's going to end up happening is that it's going to be the same at 0.3 plus as it was at 0.3 minus. It's going to be the 2.11 volts. Now it's very important that in this case, yes, the function we're looking for, V0, had the same value before the switch and after the switch, but unless that thing in general is the voltage across capacitor or current through inductor, we will not normally know that they're the same, and you should go through this whole analysis I just did right here to the end of showing that they're the same in this particular case. But if that capacitor had been in series with the resistors, it would not have turned out to be the same there. So you got to be very careful in these problems. Just warning you right now, because you might see some in the future where the value before the switch and after the switch are in fact different. Okay, so we have this here. We have our value of that. Now we can take the value at infinity. So, and this is the really infinity because it is going to stay 0 for all that time. So we're going to go ahead and replace the capacitor with an open for being in steady state. However, in this case here, because there is no source, nothing providing power, we know that my V0 of infinity is going to be 0 here. Now we need to find our time constant. Now our time constant is based on R Thevenin. And in this particular case, the R Thevenin is still the same after the switch as it was before the switch. Because at 0.3, there was no real connections that changed. You still have the same resistors in the same pattern. So it's still going to be 4 kilo ohms, which means my tau is still the same of 0.4 seconds here. And so we can go ahead and say V0 of 0.3 is now, it's slightly different when you're switching point as a time other than t equal to 0, and we'll see that in our final answer here, but it's still going to be k1 plus k2, so it's going to be 2.11, and v0 of infinity is still going to be just k1 is 0. So when we write out our final answer here, this is where it's going to change. 0 plus 2.11 e to the minus, now instead of just t over tau, it's going to be t minus the switching point over tau. And so for our final answer here, we have our piecewise function. It starts out as 4 minus 4 e to the minus t over 0.4 for any value of t up to 0.3. And then after that, it switches to 2.11 e to the minus, parentheses here, t minus the switching time over the time constant for any t value bigger than 0.3. So when you have switching happening more than once, I wouldn't necessarily say it's any harder than a switch only happening one time. It's the exact same process, but it just doubles your work. You have to do the same process 2 full times and get 2 answers there, and it's definitely a lot more tedious and involved to do it. Usually the numbers work out even worse, like we did here, than in a standard problem. And the thing is, even in any real-world circuit, you're probably going to have even more than 2 switches. Maybe it's going to keep switching on and off every 0.3 seconds. It's blinking or something. And so in a real-world problem, you'd probably have even more stuff going on than this. Thankfully, that's what computers are for, to solve them. We're just trying to get the handle on how this works. So when 2 switches happen, you apply the whole process twice, and then you break it down piecewise to give your final answer.